Welcome to our comprehensive exploration of DevOps concepts. DevOps represents a fundamental shift in how we approach software development and operations. This course will take you on a journey through the essential concepts, tools, and practices that make DevOps successful. We'll explore everything from continuous integration and deployment to monitoring and testing practices, ensuring you have a solid foundation in modern software delivery methods. The concepts we'll cover aren't just theoretical, they're actively used by leading technology companies worldwide. Companies like Amazon, Netflix, and Google have demonstrated how DevOps practices can enable rapid innovation while maintaining system reliability. In this session, we'll examine real-world examples and practical applications of these concepts. As we progress through the material, you'll learn how to implement these practices in your own organizations. Whether you're part of a small startup or a large enterprise, the principles and practices we'll discuss can be adapted to your specific context. By the end of this course, you'll have the knowledge and confidence to begin implementing or improving DevOps practices in your environment. Remember, DevOps is not just about tools or processes, it's about culture and mindset. We'll discuss how to foster collaboration between development and operations teams, how to build a culture of continuous improvement, and how to measure and demonstrate the value of DevOps practices to stakeholders. We're about to delve into one of the most transformative aspects of modern software development, CI/CD pipelines. Continuous integration and continuous delivery/deployment have revolutionized how we build, test, and deploy software. This transformation isn't just about speed, it's about reliability, quality, and confidence in our software delivery process. Throughout this section, we'll explore how to achieve similar transformations in your own organizations. We'll examine the technical components that make up a CI/CD pipeline, the tools that enable automation, and the practices that ensure success. You'll learn how to build pipelines that can handle everything from simple applications to complex microservices architectures. The concepts we'll cover here form the foundation for modern software delivery. Whether you're working on web applications, mobile apps, or enterprise systems, understanding CI/CD will be crucial to your success. We'll explore how companies like Amazon and Google use these practices to deploy thousands of times per day while maintaining high reliability and customer satisfaction. As we progress through this section, keep in mind that implementing CI/CD is a journey, not a destination. We'll discuss how to start small and gradually expand your pipeline's capabilities as your team's confidence and expertise grow. Let's dive deep into the intricacies of building and testing in modern software development. This knowledge forms the cornerstone of reliable software delivery, and mastering these concepts will significantly impact your ability to deliver high-quality software consistently. Build configuration represents our first critical component. Modern applications require sophisticated build processes that handle multiple dependencies, environment-specific settings, and various deployment targets. Using tools like YAML and JSON, we define these configurations as code, enabling version control and automation. For example, a typical build configuration might specify environment variables that change between development, staging, and production, dependencies and their specific versions, build steps for different components of the application, resource allocations and timeout settings, security scanning and code quality checks. Automated testing forms several layers of protection against defects. Unit testing verifies individual components in isolation. Think of testing a payment processing function with various input combinations. Integration testing ensures different components work together correctly, like verifying that the payment processor integrates properly with the order management system. End-to-end testing validates complete user journeys, such as a customer completing an entire purchase flow. Popular test frameworks provide the foundation for these different testing types. JUnit and TestNG excel in the Java ecosystem, while PyTest offers powerful features for Python applications. Selenium enables comprehensive web application testing, and Cypress provides modern alternatives for front-end testing. Each framework has its strengths, and we'll explore how to choose the right tools for your specific needs. Test coverage metrics help us understand the effectiveness of our test suite. Tools like JaCoCo and Istanbul provide detailed reports showing which parts of our code are exercised by tests. However, it's crucial to understand that coverage numbers alone don't guarantee quality. We need meaningful tests that verify business-critical functionality. Code quality tools add another layer of protection. SonarQube analyzes code for potential bugs, security vulnerabilities, and maintainability issues. ESLint ensures consistency in JavaScript code. Together, these tools help maintain code quality standards across large teams and complex codebases. Managing artifacts and dependencies represents another crucial aspect of the build process. For example, in a microservices architecture, different services might share common libraries. Proper artifact management ensures teams use consistent versions of these shared components. Tools like Artifactory or Nexus provide secure repositories for storing and versioning these artifacts. Let's delve into the crucial distinctions and practices that define modern deployment and monitoring strategies. The choices we make in these areas directly impact our ability to deliver reliable software and maintain it effectively in production. First, let's clarify the important distinction between continuous delivery and continuous deployment. Continuous delivery ensures our code is always in a deployable state, with automated testing and staging environments verifying readiness. However, the final deployment decision remains manual. This approach suits organizations with regulatory requirements or those needing additional validation steps. Continuous deployment takes automation one step further, automatically deploying verified changes to production. This approach, used by companies like Amazon and Google, enables multiple deployments per day. However, it requires sophisticated automated testing and monitoring to ensure reliability. Various deployment strategies help manage risk during releases. Rolling updates gradually replace instances of our application, enabling smooth transitions with minimal downtime. Blue-green deployments maintain two identical environments, allowing instant rollback if issues arise. Canary releases expose new versions to a subset of users first, helping catch problems before they affect everyone. Infrastructure as Code, IAC, represents a fundamental shift in how we manage deployment environments. Using tools like Terraform or CloudFormation, we define our infrastructure through code, enabling version control and automated provisioning. This approach eliminates environment inconsistencies and enables rapid scaling. Containerization technologies like Docker and Kubernetes have revolutionized deployment practices. Containers ensure consistency between development and production environments, while Kubernetes provides sophisticated orchestration capabilities. These tools enable efficient resource utilization and simplified scaling strategies. Monitoring forms the feedback loop that ensures our deployments succeed and continue performing well. Tools like Prometheus excel at metrics collection, while Grafana provides powerful visualization capabilities. New Relic offers comprehensive application performance monitoring, helping identify and diagnose issues quickly. Post-deployment testing validates our changes in production conditions. Smoke tests verify critical functionality immediately after deployment. Performance testing ensures our changes maintain expected response times under load. Regression testing catches any unintended impacts on existing functionality. The key to success lies in implementing these practices systematically. Start with basic monitoring and gradually expand coverage. Begin with simple deployment strategies and evolve as team confidence grows. Remember, the goal is to enable rapid, reliable software delivery while maintaining system stability. Welcome to our exploration of logging, monitoring, and alerting, collectively known as LMA. These three pillars form the foundation of observability in modern systems, enabling teams to understand system behavior, detect issues early, and respond effectively to incidents. The practices we'll discuss in this section have evolved through years of operating complex systems at scale. Organizations like Google, Amazon, and Netflix have pioneered many of these approaches, demonstrating their effectiveness in maintaining reliable services while moving quickly. As we explore these topics, we'll examine how each component contributes to system observability and how they work together to provide a complete picture of system health. Whether you're managing a single application or a complex distributed system, the principles we'll discuss will help you implement effective observability practices. Remember, the goal isn't just to collect data, it's to gain actionable insights that enable better decisions and faster problem resolution. Throughout this section, we'll focus on practical approaches that you can implement in your own environments. Logging serves as our system's black box recorder, providing crucial insights into application behavior and helping diagnose issues when they occur. Let's explore how to implement effective logging practices that support both development and operations teams. Different types of logs serve different purposes in our observability strategy. Application logs capture business events and technical operations within our code. System logs provide insights into infrastructure behavior, including resource utilization and security events. Security logs track authentication attempts, authorization decisions, and potential security incidents. Log formats play a crucial role in making our logs useful. Plain text logs might work for simple applications, but structured formats like JSON enable better parsing and analysis. The syslog standard provides a common format for system and network device logs. Choosing the right format depends on your tools and analysis needs. Log levels help categorize information by importance and purpose. Debug logs provide detailed information for development and troubleshooting. Info logs track normal system operations. Warning logs indicate potential issues that deserve attention. Error logs capture failed operations that require investigation. Critical logs demand immediate attention, often triggering alerts. Log aggregation and centralized logging transform individual log entries into actionable intelligence. Tools like the Elk Stack, Elasticsearch, Logstash, and Kibana enable collection, storage, and analysis of logs from multiple sources. This centralization enables correlation between events across different system components. Best practices for logging include consistent formatting across all application components, clear, descriptive messages that provide context, inclusion of relevant metadata like request IDs and timestamps, appropriate use of log levels to maintain signal-to-noise ratio, proper handling of sensitive information to maintain security, regular log rotation and retention policies to manage storage. Common logging frameworks provide sophisticated features for implementing these practices. Log4j and Logback in the Java ecosystem offer powerful configuration options. Winston for Node.js enables flexible logging formats. The Python logging module provides comprehensive logging capabilities out of the box. Monitoring provides real-time visibility into system health and performance, enabling teams to detect and respond to issues before they impact users. Let's explore how to implement effective monitoring strategies that support reliable system operations. Application performance monitoring helps us understand how our software behaves in production. This includes tracking response times, error rates, and resource utilization. For example, in a web application, we might monitor page load times, API response times, and database query performance. These metrics help us identify bottlenecks and optimize user experience. Infrastructure monitoring ensures our underlying systems have the resources they need to operate effectively. This includes tracking CPU usage, memory consumption, disk space, and network performance. Modern cloud environments add additional metrics like container health, auto-scaling events, and cloud service performance. Understanding these metrics helps prevent resource-related outages and optimize infrastructure costs. Network monitoring provides insights into connectivity and data flow between system components. This includes monitoring network latency, bandwidth utilization, and packet loss. In distributed systems, network monitoring becomes crucial for maintaining reliable communication between services. The choice of monitoring tools depends on your specific needs and environment. Prometheus has become a standard for metrics collection, offering a powerful query language and extensive integration options. Nagios provides comprehensive infrastructure monitoring capabilities. Grafana enables sophisticated visualization and dashboarding of metrics from multiple sources. Real-time monitoring enables immediate detection of issues, while periodic monitoring helps identify trends and patterns over time. For example, real-time monitoring might alert us to a sudden spike in error rates, while periodic monitoring helps us understand capacity needs for future planning. Setting appropriate thresholds for monitoring metrics requires careful consideration. Too sensitive, and you'll generate noise that masks real issues. Too lenient, and you'll miss important problems. The best approach often involves establishing baseline performance through observation and gradually refining thresholds based on experience. Modern monitoring systems often incorporate machine learning to detect anomalies automatically. These systems can identify unusual patterns that might not trigger traditional thresholds but could indicate emerging problems. For instance, they might detect subtle changes in user behavior patterns that predict upcoming system issues. Alerting turns monitoring data into actionable notifications, ensuring the right people receive critical information promptly. Let's explore strategies for effective alerting to support rapid incident response while avoiding fatigue. Modern alerts provide context and actionable insights for quick decision-making. For instance, instead of merely flagging high CPU usage, an alert should indicate affected services, normal ranges, and recent contributing changes. Differentiating alerts from notifications is key. Alerts demand immediate attention for service-impacting issues, while notifications convey important but non-urgent information. This distinction helps teams prioritize responses effectively. Different alerting mechanisms serve distinct purposes. Email is suitable for non-urgent notifications and detailed reports. SMS and calls ensure critical alerts reach on-call personnel swiftly. Tools like Slack facilitate team discussions, while PagerDuty supports on-call management and escalation. Managing alerts involves clear processes, including severity levels, response procedures, and escalation paths. For example, a Severity 1 alert may require immediate response and escalation if unacknowledged, while Severity 3 issues can wait for business hours. Escalation ensures alerts receive attention when primary responders are unavailable. This includes engaging backup engineers, involving teams, or notifying management based on incident severity and duration. Defined paths prevent overlooked alerts. Effective alerting policies balance urgency and issue impact, team capacity and resources, on-call schedules and business hours, technical investigation tools, historical patterns and known issues. Integration between monitoring and alerting systems allows sophisticated notification rules. Combine metrics to reduce false positives, use delay timers for transient issues, or adjust thresholds by time or load. Best practices include clear, actionable alerts with context, consistent severity levels across systems, on-call rotation to avoid burnout, regular threshold reviews and refinements, documented response procedures, post-incident reviews for improvement. Structured alerting can significantly improve outcomes. One organization cut acknowledgement times by 70% through better policies, while another reduced weekend callouts by refining thresholds and escalation processes. As we transition to behavior-driven development, or BDD, We're entering a domain that fundamentally changes how teams collaborate on software development. BDD represents more than just a development methodology. It's a communication framework that bridges the gap between technical and non-technical stakeholders in software projects. For various organizations, BDD has consistently proven its value in reducing requirement misunderstandings and improving software quality. One enterprise organization reduced their requirement-related defects by 40% within 6 months of adopting BDD practices. This improvement came not just from better testing, but from enhanced communication and shared understanding among team members. The principles we'll explore in this section apply whether you're working on small applications or large enterprise systems. BDD's structured approach to describing software behavior helps teams maintain clarity and focus throughout the development process. As we progress through this section, you'll learn how to implement these practices in ways that complement your existing development processes. Consider this section as your foundation for creating more collaborative, efficient development processes that deliver software matching business expectations more consistently. Writing effective BDD scenarios requires both art and science. The given when-then format provides our structure, but the real value comes from crafting scenarios that capture meaningful business behaviors and guide development effectively. Clarity and specificity in scenarios prove crucial for success. Consider a banking application rather than a vague scenario about funds transfer. An effective scenario would specify, given a customer has $0.00 in their savings account, when they transfer $0.00 to their checking account, then their savings balance should be $0.00, and their checking balance should increase by $0.00. This level of detail eliminates ambiguity and provides clear acceptance criteria. The process of identifying meaningful scenarios often reveals important business rules and edge cases. During a project for an insurance company, scenario workshops uncovered several business rules that weren't documented elsewhere. This discovery prevented potential issues before development began. Business requirements mapping to scenarios requires careful consideration. Each requirement should be represented by one or more scenarios that demonstrate the expected behavior. Working with a telecommunications company, we developed a requirement mapping matrix that helped ensure comprehensive coverage while avoiding duplicate scenarios. Collaborative scenario development brings multiple perspectives to the table. Business analysts contribute domain knowledge, developers identify technical considerations, and testers think about edge cases and validation requirements. This collaboration often reveals assumptions and potential issues early in the development process. The importance of focusing on behavior rather than implementation details cannot be overstated. Scenarios should describe what the system does, not how it does it. This approach ensures scenarios remain valuable even as implementation details change over time. Test-driven development represents a fundamental shift in how we approach software construction. Rather than viewing testing as a validation activity that occurs after development, TDD places testing at the heart of the development process itself. In this section, we'll explore how TDD changes the development workflow, improving both code quality and developer confidence. We'll examine real-world examples of TDD implementation and discuss strategies for adopting TDD in different development contexts. The principles we'll cover apply whether you're developing new features or maintaining legacy code. TDD provides a structured approach to development that helps ensure code quality and maintainability from the start. Test-driven development fundamentally changes how we write software. Instead of writing code first and then testing it, we begin with tests that define the desired behavior. This approach, while initially counterintuitive, leads to better design decisions and more maintainable code. The red-green refactor cycle forms the core of TDD. First, we write a failing test, red, that defines the desired behavior. Then, we write the minimum code necessary to make the test pass, green. Finally, we improve the code while keeping tests passing, refactor. This cycle ensures we maintain focus on delivering working, well-structured code. TDD differs from traditional development approaches in several key ways. Rather than writing large blocks of code and then testing them, TDD encourages small, incremental changes driven by tests. This approach reduces debugging time and makes it easier to identify when and where issues occur. The benefits of TDD extend beyond just catching bugs. TDD encourages better software design by forcing developers to think about interfaces and behavior before implementation. When implementing a new feature for a payment processing system, starting with tests helped our team identify and resolve design issues before writing production code. Common misconceptions about TDD often include believing it slows down development or requires writing tests for everything. In practice, TDD can actually speed up development by reducing debugging time and preventing rework. The TDD process follows a structured workflow that guides developers through the development cycle. Understanding this workflow and its principles helps teams implement TDD effectively and consistently. Writing test cases before implementation requires a shift in thinking. Instead of asking, "How will I implement this feature?" we start by asking, "How will I know when this feature works correctly?" This shift leads to clearer requirements and better defined functionality. Good unit tests share several characteristics. They should be focused, testing one specific behavior or scenario. They should be independent, not relying on other tests or external state. They should be readable, clearly expressing their intent. And they should be fast, enabling quick feedback during development. Test fixtures play a crucial role in TDD by providing consistent test environments. When developing a customer management system, we created fixtures that provided standard test data for different customer scenarios. This approach ensured consistent testing across the development team. Test doubles, mocks, stubs, and fakes enable isolated testing of components. For example, when testing an order processing system, we used mocks to simulate database interactions, allowing us to test business logic independently of the actual database. This approach led to faster, more reliable tests. The refactoring phase of TDD deserves special attention. With a comprehensive test suite in place, developers can confidently improve code structure without fear of breaking functionality. One team improved their application's performance by 30% through aggressive refactoring, confident that their test suite would catch any regressions. Service mesh technology represents a significant advancement in how we manage service-to-service communication in modern distributed systems. As applications grow more complex and distributed, Service Mesh provides the control and visibility needed to operate these systems effectively. While implementing some Service Mesh solutions, the benefits become particularly apparent as organizations scale their microservices architectures. One organization reduced their mean time to resolution for production incidents by 50% after implementing a Service Mesh, thanks to improved visibility and control over service communication. This section will explore how Service Mesh technology addresses common challenges in distributed systems, including service discovery, load balancing, and observability. We'll examine real-world implementations and discuss strategies for adopting Service Mesh in your own environment. The concepts we'll cover are essential for anyone working with modern distributed systems, particularly those built using microservices architecture. Service Mesh technology has evolved to address the growing complexity of service-to-service communication in modern distributed systems. Understanding its components and architecture is crucial for successful implementation. The evolution of Service Mesh came from real needs in operating microservices at scale. Traditional networking approaches struggled to handle the complexity of modern distributed applications. Service Mesh provides a dedicated infrastructure layer that handles service-to-service communication, enabling better control and visibility. Key components of a service mesh typically include a data plane, which handles actual request traffic, and a control plane, which manages mesh configuration and policy. This separation of concerns enables efficient operation and management of the mesh. Popular implementations like Istio, Linkerd, and Consul each offer distinct advantages. Istio provides comprehensive features but requires more resources to operate. Linkerd emphasizes simplicity and performance. Consul integrates well with existing HashiCorp tools. Understanding these differences helps in choosing the right solution for your needs. Service mesh benefits extend beyond just technical improvements. One organization improved their ability to diagnose production issues by 60% after implementing service mesh, thanks to improved observability and debugging capabilities. Another team reduced their service deployment time by implementing automated canary deployments through their service mesh. Welcome to our exploration of service mesh features and functionality. Today, we'll examine the essential capabilities that make service meshes fundamental to modern cloud-native architectures. Service discovery and load balancing form the foundation of service mesh functionality. In complex microservices environments, these features ensure that services can locate and communicate with each other efficiently while maintaining optimal traffic distribution across service instances. The traffic management and routing capabilities provide sophisticated control mechanisms. Service meshes enable dynamic route configurations, traffic splitting for A/B testing, and request routing based on various attributes. These features are particularly valuable when implementing progressive delivery strategies. Circuit breaking and fault tolerance mechanisms help maintain system stability. When issues arise, the service mesh can automatically redirect traffic to healthy instances and implement retry policies with exponential backoff, preventing cascade failures across your system. The observability and monitoring tools provide unprecedented visibility into your service network. By collecting detailed metrics about request volumes, latencies, and error rates, teams can make data-driven decisions about system optimization and troubleshooting. Security features include automated mutual TLS implementation and granular access control policies. This ensures consistent security practices across your entire service network without requiring changes to application code. Finally, distributed tracing capabilities allow you to track requests as they flow through multiple services, making it easier to debug issues and optimize performance. This visibility becomes increasingly valuable as your system grows in complexity. I encourage you to experiment with these features in a test environment, starting with basic traffic management and gradually exploring more advanced capabilities. This hands-on experience will prove invaluable as you work with production microservices architectures. Let's wrap up this comprehensive session on service mesh features and functionality. Today, we've covered fundamental aspects that are crucial for modern distributed systems architecture. We began by exploring service discovery and load balancing, understanding how these features form the backbone of reliable service-to-service communication. We then delved into traffic management and routing capabilities, which give you fine-grained control over how requests flow through your system. We examined the critical role of circuit breakers and fault tolerance mechanisms in maintaining system stability, and how observability tools provide the visibility needed to manage complex distributed systems effectively. We also covered the robust security features that service meshes provide, including MTLS and access control. The deployment strategies we discussed, particularly canary and blue-green deployments, showed how service meshes facilitate safe and controlled application updates. Finally, we explored distributed tracing and its importance in understanding and optimizing system behavior. Key takeaways from this session: 1. Service meshes provide essential infrastructure for modern microservices architectures. 2. They offer a comprehensive suite of features that would be complex to implement individually. 3. The observability and security features are particularly valuable for production environments. Deployment strategies become more manageable with service mesh capabilities. As you move forward, I encourage you to set up a test environment with a service mesh. Istio is a good starting point. Experiment with different traffic routing scenarios. Practice implementing security policies. Use the observability tools to understand system behavior. These skills will be invaluable as you work on microservices architectures, cloud-native applications, system reliability engineering, platform engineering roles. Remember, the concepts we've covered today are increasingly important in the job market, particularly for roles involving cloud-native architecture and DevOps practices. Many organizations are adopting service meshes as they move toward microservices architectures, making this knowledge particularly valuable for your career growth.